Hi, my name is Jack Ridge, and I'm a geologist in the Earth and Ocean Sciences Department at Tufts University. And I've been doing field work in the fells to try to understand what rock formations are there and their relative ages. And this is a perfect place for doing it. We're on the top of Gerry Hill on the Skyline Trail, where there are two rock formations exposed. One of them is the Virginia Wood quartzite, which is what I'm sitting on. And it's a rock formation composed of layers, this light layer right here, of a rock called quartzite, which is metamorphosed sandstone, made up mostly of tiny grains of quartz that have been heavily stretched. In that rock unit, a rock type is in another unit that has all kinds of fine lines and partings. And this is a rock type called argillite, which is a very hardened shale or mudstone. And it has all kinds of lines in it which were produced by the rock shearing as a result of metamorphic activity and mountain building. So we're in another part of the outcrop on Gerry Hill where we see a second rock unit. That's this material right in front of me that has sort of an oatmeal type texture to it. This is the spot pond granodiorite, which is made of large crystals of quartz and two different types of feldspar. This rock unit started as magma that slowly crystallized into the subsurface, producing the quartz and feldspar crystals. So one of the things that we were worried about is, well, what are the ages of the rock units on this outcrop? If you look here just to my right, you'll see a piece of quartzite that is floating in the granodiorite, which is on both sides of it. So this is a piece of quartzite that broke off into the granodiorite magma, and then when the magma froze or crystallized, it trapped that fragment. We call that an inclusion. So that gives us solid evidence that the quartzite unit is older than the granodiorite. Okay, so what we just did is we figured out the relative ages of two rock units. We have the spot pond granodiorite, which is younger than the inclusions of the Virginia Wood quartzite. So that has to be from an older unit. Now the other thing we want to know is how old are these rock units numerically? Now nowadays we can do that by taking a sample of the rock unit. So first of all, let's talk about the granodiorite. We can take a sample of this unit and crush it to a fine sand size. And when we do that, tiny crystals of zircon separate from the rock. Zircon is zirconium silicate. Now there's not a lot of zirconium in this rock, but what zirconium is here, it does crystallize as tiny zircon crystals. So we can separate those, and they're really, really hard. And so we take those crystals, which have trace amounts of uranium in them when they first crystallized in the magma. That uranium decays to lead. So we can measure different isotopes of lead and different isotopes of uranium and figure out how long that zircon crystal has been in existence. And that gives us the age of the spot pond granodiorite, which turns out to be 610 million years. That places it in a time period called the late Proterozoic. So now, how do we figure out the numerical age of the quartzite? We know that it has to be older than 610 because it comes from an older rock formation. But we can also crush the quartzite and take little zircon crystals, which were sand grains in the original sandstone. Now, those zircon crystals didn't form in the sandstone. They are inherited from older rock units that eroded, that had zircon in them. So when we take the ages of those zircons, they're going to be a whole bunch of ages up to a point. So in the quartzite, we only see zircon crystals that are as young as 930 or older. And what that tells us is that the quartzite cannot be older than that. It cannot be older than the zircon crystals that it inherited from the erosion of older rocks. So that puts a time frame on the geology. So here we know we have an igneous rock that's 610, and we have a metamorphic rock that is 930 or younger. It has to be somewhere between 610 and 930 million years. All right. An interesting footnote to all of this is that these rocks are very old and they have moved quite a bit from where they originally formed. The process of plate tectonics on the planet is constantly splitting apart continents and moving them to different locations. Sometimes these continents collide with each other and become new continents. And that's what happened a long time ago in the Boston area. A section of Northwest Africa peeled off of what is today Northwest Africa and headed across an ancient ocean and collided with rocks that were already in North America. That section of rocks from Africa was what we call the Avalon terrain, and it arrived here somewhere in the neighborhood of about 400 million years ago or so. More recently, there's another geologic event that occurred here on Gerry Hill. During the last ice age, there was a mile of ice sliding across the land surface, dragging debris across the rock surface. And what it did is it put all kinds of scratches and grooves on the rock surface. And also the fine material that was between the ice and the rock surface polished that rock surface. So if we look down, we can see places like right here that we wet so that you could see it a lot better, but there's all kinds of fine scratches and grooves on the quartzite unit right here that are running in this direction, which was the direction in which the ice was sliding across the rock surface. So that direction is about south 20 degrees east. In other words, 20 degrees just to the east of south. The ice was heading to the south out towards the ocean.
If you want to learn more about Professor Ridge's research on the geology of the fells, including a map and self-guided geologic hikes, follow this link to his website.